Let's consider a particular function. And we start with drawing a tangent plane to its graph. And as for the point we're choosing, let it be x0, y0, 1, 1. Then z0 can be found by substituting for x and y. So when we have also 1. Now let's draw the graph. So the graph resembles, it has the shape of a hill. So the top is at the origin, so this is the origin. Here we have 3. And there is a point here, which is 1, 1. And the corresponding z0 is somewhere here on the surface. So the tangent plane, well, clearly I will draw simply a piece of it. So it touches the surface at this particular point. What's important is that when we compare the values which lie on the surface with the values for the same xy values which belong to the tangent plane, they're very, very close. We need to refresh some ideas about planes in 3D. So a Cartesian equation of such a plane can look like z minus z0 equals a is a number, x minus x0 plus b, y minus y0. So for any a,b values, this is a plane which passes through the point with coordinates x0, y0, and z0. What we can say about this particular tangent plane? There is a theorem which claims that we can find the equation or the tangent plane to a surface, which is a graph of a particular function, if a is the partial derivative of function f with respect to x taken at x0, y0, and b is partial derivative with respect to y taken at the same point. Let's consider a very important notion connected with the tangent plane. It is called total differential. We remember from single variable calculus that there is a differential of the independent variable dx, which is simply an increment in x. That's the definition, x minus x0. Given a function of one variable only, its dependent variable y also has a differential, dy. dy, by definition, is the product of the derivative by the differential dx. Now we deal with the function of two variables. So let's consider a function z and similar to this formula, we can give rise to the x variable, and we can keep y value fixed at the value y0. Then we have a product of df over dx times dx. But what if we give rise not only to x but also to y? Then we need to add also the product of df over dy times dy, and the sum of these two terms will give us dz, and we call it total differential of the function of two variables. Now, if you compare this formula with the formula of the tangent plane, given the values of a and b, we can compare and see it's the same formula. So it looks as if that the total differential provides the linear approximation of the function in question, f of xy.